All right, let's talk about quotient rule for exponents. So quotient rule for exponents says that if we have the same base, here it's a again, and we divide them, right, then we can just subtract the exponents. All right. So, and notice how we just end up with 1a, right? Once again, we go from two bases to one base, just like with the product rule. So let's try this example. So we have 8 to the 6th power over 8 squared. And so basically what the quotient rule says is I can end up with 1 base, right? And then I can subtract the exponents, 6 minus 2, and we get 4. So 8 to the 6 over 8 squared is just 8 to the 4th. All right. Now, if I was asked to simplify it, I'd have to take it a step further and actually evaluate 8 to the 4th. So I could either plug into my calculator 8 caret 4, or I could do 8 times 8 times 8 times 8. And so I could get that answer. But for the sake of exploration here, let's keep it in exponential form and just think about why this rule works. So let's put this expression in expanded form. If I have 8 to the 6th, that's going to be a product of 6 eighths, right? Oops. So a product of 6 eighths, and then 8 squared is a product of 2 eighths. So if I have 8's on top and 8's on bottom, I can cancel out the ones that are in common on top and bottom, right? So 8 divided by 8 would be 1. Or I can, think about dividing the numerator and denominator by 8, right? So I can cancel out those 8's and I can cancel out these 8's, right? So that leaves me with 4 8's, right? So basically that's what we're doing when we're doing the quotient properties. We're just saying, okay, well, if I have 6 8's on top and 2 8's on the bottom, then I'll end up with 4 8's on top, right? So you're just subtracting essentially the 8's that you have in common on top and bottom. So that's how the quotient rule works. All right, let's see it in practice. Actually, there we go. All right, so let's check out number 24. So remember, our property says if we have a to the m divided by a to the n, that equals a to the m minus n. So when we divide bases, we subtract the exponents, right? And they have to be like bases. All right, so now remember, division can be written a few different ways. So another way that we could write this property is a to the m divided by a to the n equals a to the m minus n. So we can use the division symbol, this division symbol, right, as well. So that comes into play on 24. We're dividing like bases. Both the bases are a, so we can simplify that to a single a and subtract the exponents. 12 minus 3 is 9, so we get a to the 9th. All right, so that's it. 26, same idea. We're dividing like bases, both w's there, so we can get that down to one single w, subtract the exponents. 12 minus 6 is 6. So w to the 6 is our final answer. 28, we're dividing q to the 5th divided by q to the 5th. So q's are common or like bases, so we can end up with a single q, subtract the exponents. 5 minus 5 is 0. Okay, and then we know from our last rule, anything to the 0 power is 1. So we can just simplify the whole expression to 1. All right, now, by the way, that's one that we could do intuitively, right? When we divide anything by itself, we get 1. So that would have been another way to do it. All right, number 30. Here we have constants in the mix, right? So just do what we normally would. 8 divided by negative 2, still 8 divided by negative 2, right? Those are not exponents, so we don't use exponent properties with these because they're just normal bases. Or excuse me, they're just constants. So 8 divided by negative 2 is negative 4. Then we'll deal with our m's because those are like bases. So we're going to bring over a single m. We're going to subtract the exponents. 17 minus 13, that equals 4. So we get negative 4m to the fourth. 32, similar idea. Negative 22 divided by negative 11. We're going to deal with the constants first. That equals 2. Okay, now I have v's, right? So I'm going to deal with those next. So v cubed over v squared, I'm going to end up with 1v. And then I'm going to subtract their exponents, 3 minus 2. That equals 1. But remember that anything to the first power is itself, right? So v to the first power is just v. So I'm just going to leave the 1 out and put it in its simplest terms. Next, we'll address the w's. So we have w to the 9th over w cubed. Bring over w. We're going to subtract the exponents, 9 minus 3. That equals 6. And so we get 2vw to the 6th. Okay, so you basically just can compartmentalize each set of like bases or like terms and just do one part at a time and just put it all together at the end, okay? All right, so last but not least, 34. So here I have negative 51 over 17. So when I divide those, get negative 3. Then we'll address the y's. Y to the 16th over y to the 9th is, we'll bring it down to a single y. Subtract the exponent, 16 minus 9 is 7. Now for the z's, z cubed over z cubed. That equals 1, right? Anything over itself is 1, so you can just cancel those out. Or you can write, we could also subtract 3 minus 3. And so we would get z to the 0. But anything to the 0 power would also cancel out to 1. So anyway, so our final answer, one way or the other, is negative 3y to the 7th.